Chapter 8, Modeling with Mechanics. So, mechanics deal with the more objects, motion, and the forces. So, those are the main area combination of these three object, motion, and forces, which are dealt in mechanics. And the object can be just one object or set of object. For example, a car. Car is usually denoted by a small box in mechanics. So it can be a car or it can be a couple of vehicle towing by a rod. So set of object and motion and stationary. We know any object in this space, any object have two status. One is motion and the other one is stationary. You can't find anything apart from that two status. So if you consider football either it is in a stationary position or it is in a motion, maybe in air, or it is rolling around the ground with the rotation around the ground. And sometimes apply forces or without. So apply forces, for example, there are two status. The object can be in either it is motion or stationary. If it is in a motion, if you apply a force, so for example, the ball is coming, ball is moving along this direction, and if you apply a force or kick to here, what will happen? It may change the direction and the speed. That's the only thing can happen. It may change the direction, the speed, or uh, if something in the motion, if the football is in a stationary, then if you apply a force, so it can make a move if this force is strong enough. Otherwise, still stay the same. Sometimes instead of one force, there may be more forces in this direction and the other direction. Maybe here, if two people kick to the ball, it means two forces are applied on the ball. Let's discuss the modeling process. Um, ini- Initially, we specify the problem, real world issue. Then sometimes we apply assumptions to make it simple. For example, if it is a ball, sometimes we will consider as a particle. Sometimes string, we will take that is a light string. So then we can, the weight is disregarded when we use the word light, or space, a smooth space. The word smooth disregard the friction. Likewise, we are applying assumptions to make it simple. Then we set up a mathematical model. Set up a mathematical model. If we throw in a ball, the path of a ball, this is similar to the parabola of we know this one. This is a quadratic equation, and ax square plus bx plus c y equal, and a value is negative. That's why we get a maximum. Then uh, we have to adjust these values. So likewise, we can set up a mathematical model for this one. For this part, we will tell that okay, y equal ax square plus bx plus c form. Then solve the model. In in here, specify the real world issue. So we should be uh, this should be a clear statement of a situation and should specify the result required in the solution. So we know what we need exactly. So we are defining here, and then we solve the model. Sometimes solving mean we are giving some values. Y equal minus 3x square plus 4x plus 2. Likewise, we giving some values. And then we want to check this values is correct. Then that is where we need the experimental data. So obtain uh, experimental data. So when we get experimental data, so we need to compare with the real life situation, and we want to check the errors, quantify errors. Then we will come to a conclusion that is this model is this model is good enough. So if not, we have to go the same process again. See, we want to look at our assumptions is right and the model, and so we have to go to the same process if it's not. So if it is fine, then we just write a report on it. Write a report. So this is happening everywhere. Another example is assume that engineers want to make this is a uh, big project, make a bridge, then lot of assumptions, and then draw a model, and then they evaluate it with the computer, and then yes, they simulate with the computer and see they have to readjust their design, and yes, if it is yes, they will build it, otherwise they will go this process again. In mechanics, there are two type of mechanics. What the first one is classical mechanics. The other one is quantum mechanics. Quantum is a recent development. Uh, we initially work with the classical mechanics. Sometimes this is we name that Newton mechanics as well, because the Newton gave a good start with the Newton law to the mechanics. It is very important to know that the Newton laws in the mechanics. Those are the laws we are going to use on everywhere in the mechanics. In classical mechanics, there are so many branches. You can You can find information from the web, which I'm not going to discuss. Now we will discuss the Newton laws. Newton first law. Every object remains at rest or move with a constant velocity unless an external force is applied. So this is true. Every object remains at rest, or either it should be in motion. But here there is a word constant velocity. The good example is if we throw a ball in this air, so there it is not in constant velocity because it will fall if we throw because of the gravity, and there is air resistance, so it will slow down the speed, and as a result it's come to the stationary. But if there are any if there is no any external force acting on in a moving object on a moving object, then it keep that constant velocity. uh, the good example, the best example is we can't find anything move with a constant velocity in day-to-day life in our nature because of this air resistance and the gravitational force. But if you consider the earth and the ozone layer, then the above ozone layer empty space. So in empty space, any particle uh, is floating around with the same velocity. Assume if we manage to send a particle from Earth to this empty space, and when that particle getting into the empty space, assume that the speed is 1200 kilometer per hour, then after that it is whole universe moving until it hit, or yeah, until it change the direction by acting a force by collision with some other thing. Apart from that, it is moving on this constant speed. So this is the best example uh, that the Newton is mentioning. That is constant velocity. Next one is Newton second law. The Newton second law: a force acting on an object is proportional both to the acceleration and to the mass of the object. A force acting on an object. This is the object. A force is acting on it. F. This F is proportional to assume that it's move with the acceleration A and the weight is M. Not weight is M. Mass. The mass is M. Then F is proportional to the mass of the object, and this was also proportional to the acceleration. So it means that this is proportional to both acceleration and mass. Now we can take this proportional out by putting a constant as usual. and we found that k equal 1, then the formula is going to be F equal ma. The SI unit of force is Newton. So we use N letter. So we define is like this. So this is the equation F equal ma. So we set m equal 1 kg and acceleration is 1 meter per second, 1 meter per square second. So then this is going to be 1 times kg times 1 times ms minus 2. This is going to be 1 times kg ms minus 2. So this is we define as 1 Newton. In other way, 1 Newton means force needed to accelerate a 1 kilogram mass at 1 meter per square second. Assume we have a mass with 1000 kg and I want to give an acceleration of 2 ms minus 2, then I want to find the force. Find the force. So equation equal ma. So m is 1000 and then this one is 2. So the required force is 2000 Newton. Assume if I have a object, I give 2000 Newton and I need 4 ms. It will gain 4 square meter, 4 meter per second, square second, and I want to find the mass m. So F equal ma. F is 2000 and m we don't know. A is 4, then m is 2000 divided by 4. This is going to be 500 kg. Important thing is F equal ma is a vector equation. So when you apply this one, you have to show the direction, which direction you are going to apply. For example, assume we have object and we have a force F1 force like this and another force I apply with F2 with 45 degrees. Then then it's different. We have to work differently. We will discuss in the next sections. So then we have to get the component of F2 and we have to select the direction F equal ma to this direction. Then it's going to be if this direction we have a force as F1 and then we have to accumulate F2 cos 45 equal m times for this direction A. I will take that direction A1. Sometimes this one is moving to this direction. So then I consider this one and also we want to take here F equal ma to downwards, then this is going to be f2 sine 45 equal m times a2. So a2 is the acceleration for this direction. Then if you need to find the total the direction, so then you have to work out the total. So a1 is here and a2 is here. then also known as a resultant acceleration. You can't understand this one yet, just leave it, we'll discuss. Newton's third law. This is a very famous one. For every action, for every action, there is an equal and opposite reaction. Assume if you throw a ball to the wall, so this ball will hit with a, uh force. Let the size of force is alpha, and to this direction, then the wall will give another force to the ball with the same size but opposite. That's why wall is bouncing back. So what is the assumption here? It is a rigid ball, very tough ball. It is not a soft ball. The soft ball will absorb. If you try to push a table space, you will feel that with your hand, then you will feel that the table is pushing your hand to the uh, upward. So every reaction there is an equal and opposite reaction. We will sometimes you may not understand exactly, but we will uh, more familiarize with the future lessons more and more. We'll discuss as exercise 8A and then we'll discuss further.